In this video, we're going to focus on logarithms. We're going to talk about how to evaluate logs, how to use the change of base formula, how to expand, condense logs, solve equations, and also graph logarithmic functions. So let's begin. Let's begin with evaluating logs. What is log base 2 of 4? When you see a question like this, what you really need to ask yourself, 2 to the what power is 4? How many 2's do I have to multiply to get to 4? 2 times 2 is 4. You need to multiply 2 2's to get to 4, so the answer is 2. 2 squared is equal to 4. Now what about this one? What is log base 2 of 8? How many 2's do I need to multiply to get to 8? I need to multiply 3 2's to get to 8. So 2 to the third power is equal to 8. Therefore, log base 2 of 8 is 3. Try this one. Log base 3 of 9. 3 to the what power is 9? 3 squared is 9. So log base 3 of 9 is 2. Here's another one. What's log base 4 of 16? Log base 3 of 27? Log base 2 of 32. So 4 raised to the what power is 16? 4 squared is 16. 4 times 4 is 16. How many 3's do we have to multiply to get to 27? 3 times 3 times 3 is 27. So you need 3 3's to get to 27. 3 to the third power is 27. Now what about log base 2 of 32? How many 2's do you got to multiply to get to 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So we need 5 2's to get to 32. 2 to the fifth power is 32. Now what about log base 5 of 125? Log base 6 of 36? Log base 2 of 64? And log base 3 of 81. Feel free to pause the video and work out these examples. So how many 5's do we need to multiply to get to 125? 5 to the third power is 125. 6 raised to the what power is 36? It turns out 6 squared is 36 because you only need to multiply 2 6's to get to 36. How many 2's do we need to multiply to get to 64? So we said 2 to the fifth power is 32. If you multiply 32 by 2, you get 64. So we need 6 2's. 2 to the sixth power is 64. Now what is log base 3 of 81? It turns out that 3 to the fourth power is 81. If you multiply 4 3's together, that's 81. 3 times 3, this is 9. And these 3's turn into a 9 as well. 9 times 9 is 81. So log base 3 of 81 is equal to 4, since 3 to the fourth power is 81. Try these two. Log base 7, 49, and log base 3 of 1. We know that 7 squared is 49, so this is equal to 2. Now what is log base 3 of 1? Log of 1 is always 0 regardless of the base because 3 to the 0 power is 1. Anything raised to the 0 power will always be 1. Now if you see a question on the test that asks you to evaluate log 10, what is the answer? Whenever you don't see a base, it's assumed to be a 10. So 10 raised to the what power is 10? This is 1. Log of 10 is 1. Now what about log of 100? It turns out log of 100 is 2 because 10 squared, 10 times 10 is 100. Now what about log of 1,000? 10 to the what power is 1,000? 10 times 10 times 10, 3 times is 1,000. So 10 to the third power is 1,000. Thus log 1,000 is 3. Now what is log of 1 million? So here's a simplified way of getting the answer. Count the zeros. Here we have 1 0, so the answer is 1. Here it's 2 zeros, so it's 2. And here we have 3 zeros, so it's 3. In this example, we have a total of 6 zeros. So log 1 million is equal to 6. A million is basically 10 to the 6th power. 1,000 is 10 to the 3rd power. What about these? Log of 0.1, log 0.01, and log of 0.001. A log of 0.1 is equal to -1. When it's less than 1, it's going to be negative. Log of 0.01 is -2, and log of 0.001 is -3. Simply count the zeros, including the 0 to the left. So, knowing that, what do you think log of 0.00001 is? So if we count the zeros, 1, 2, 3, 4, 5, this is equal to -5. By the way, what do you think log of 0 and log of -5 is equal to? -5, log of -5 does not exist. You cannot have a negative number inside a log, and log of 0 doesn't exist. So the number inside of log, let's say if you have log x, x has to be greater than 0, not equal to it, but greater than 0. So you can have a 0.01 inside of a log, but you can't have 0 or a negative number. Consider this problem, log base 4 of 16. Try that one, and also try these. Log base 4 of 1/16, log base 16 of 4, and log base 16, 1/4. So what are the answers to these problems? So 4 raised to the what power is 16? We know that 4 times 4 is 16. So the answer is 2. Now all of these other answers, they contain a 4 and a 16. So this is going to be a 2 somewhere. Now 4 to the what power is 1/16. It turns out it's -2. Since 4 squared is 16, 4 raised to the -2 is 1/16. Whenever you have a negative exponent, the fraction will flip. So instead of being 16/1, it's 1/16. Now what if you reverse it? What's log base 16 of 4? So looking at the first one, log base 4 of 16 is 2/1. If you reverse the numbers, log base 16 of 4, it's going to be 1/2. Now what about log base 16 1/4? This is -1/2. So here's what you need to know. If you have a fraction within a log, the answer is going to be negative. Now the second thing you want to know, if the number inside the log, if it's bigger than the base, then you're going to have a whole number, typically a number greater than 1. However, if the base is larger, then you're going to have a fraction, a number less than 1. Try these examples. Log base 6 of 216, 6 of 1/216, log base 216, 1/6, and log base 216, 6. So how many 6's do you need to multiply to get to 216? It turns out that 6 to the 3rd power is equal to 216. So therefore, this is equal to 3. So every other answer is going to have a 3 in it. It could be negative, it could be positive, it could be a fraction. You just have to know which one is which. So which ones will be negative? The ones that have a fraction within the log is going to be negative. So we can put the negative sign for these two. And the other ones will be positive. Now, which one will contain a fraction? The ones that are going to have the fraction is when the base is larger. than what's inside the log. So these two will have a fraction. Now, it's either going to be 3 over 1 or 1 over 3. That's the only possibility. So the ones with fractions will be 1 over 3. This one is simply going to be 3, just negative 3. So whenever you have a fraction, it's negative. And whenever the base is larger, it's going to be a fraction. The 3 is going to be on the bottom. And so that's it. So if you know the first one, you could figure out the rest. Now the next thing that we're going to go over is the change of base formula. Log base a of b is equal to log base b over log a. And you could change the base to any number. So you can make it a new base, base c. So how can we apply this? So we said that log base 4 of 16 is equal to 2. If you have a calculator with you, type this in log 16 over log 4. You'll also get the answer 2. That's how you can evaluate a log that looks like this with a calculator. Just type in log 16 over log 4. You can try another example. We know that log base 2 of 8 is equal to 3. So if you type in your calculator log 8 divided by log 2, you should also get 3. Make sure you enclose these numbers in parentheses, like this. Now let's say if you have the expression log base 5 x minus y. How can you use the change of base formula to convert this log expression into a natural log? So using the change of base formula, we could say it's log x minus y over log 5. Now we could make it any base. To convert a log into a natural log, you want base e. Natural logs and logs are the same thing, but simply natural logs have the base e. Logs could have any base, 5, 7, 20, 10, it could be anything. But using the change of base formula, we can make this 7 if we want, we can make it 4, we can make it 3, we can make it r, but we're going to choose to make it e. Log base e is natural log, so this is equivalent to natural log of x minus y over natural log of 5. So that's how you can convert a log into a natural log using the change of base formula. There are some properties of logs that you need to be familiar with. For example, log a plus log b is equal to log a times b. So you can combine two logs into a single log by multiplying what's inside of the logs. Another rule you need to know is log a minus log b is equal to log a divided by log b. And also, log a squared is equal to 2 log a. So if you have an exponent, you can move it to the front. That's another property of logs. Consider the following expression: log x plus log y minus log z. How can we combine this log expression into a single log? If there's a positive sign in front, the variables will go on top. If there's a negative sign in front, it's going to go on the bottom. So it's going to be log xy over z. That's all you got to do for this particular problem. Now let's try another example. Let's say if we have log x minus log y plus log z minus log r. How would you condense it into a single log expression? So log x and log z are positive. So we're going to put x and z on top. log y and log r contain a negative sign in front. So y and r is going to go in the bottom. So it's log xz divided by yr. Here's another one. 2 log x plus 3 log y minus 4 log z. Condense the following expression into a single log. So this time we have coefficients. Right now we can't condense it into a single log because of the coefficients. So we need to use the power rule. Remember we said that log a squared is the same as 2 log a. But what we need to do is take the 2 and move it back to the exponent position. So the 2 is going to be the exponent of x, the 3 is going to be the exponent of y, and 4 is going to be the exponent of z. So it's log x squared plus log y cubed minus log z to the 4th. So now at this point we can combine it into a single log expression. So x squared and y cubed have a positive sign in front of them. And z to the 4th has the negative sign, so it's going to go on the bottom. So this is it. It's log x squared y to the 3rd over z to the 4th. Now let's try one more example on condensing log expressions into a single log. So try this one. Just like the last example, we need to move the coefficients to their respective exponent positions. So this expression is equivalent to log x raised to the 1/2 minus log raised to the 1/3 plus log z raised to the 1/4. So now at this point we can combine it into a single log expression. So x and z will be on top since they have a positive sign in front. So it's x to the 1/2, z to the 1/4. Now the y variable is associated with the negative sign, so it's going to be on the bottom. Now because we have fractional exponents, we can convert it to a radical expression. X to the 1/2 is the same as the square root of x. Z to the 1/4 is equivalent to the 4th root of z to the 1st power, or simply just z. And the cube root of y, we can write it this way. So this is the answer in radical form. How can we expand the following logarithmic expression? So this time we're working backwards. We want to expand the log into multiple logs. So log r squared s to the 5th z to the 6th power is the same as log r squared plus log s to the 5th power minus log z to the 6th. We have a negative sign since z is on the bottom. Now what we need to do is move each exponent back to the front. So the final answer is 2 log r plus 5 log s minus 6 log z. Try this one. Log cube root x squared y over z to the 4th. So how can we expand this particular expression? The first thing I would do is rewrite it as log x squared y z to the 4th raised to the 1/3. That's the same as the cube root of what's inside. So before we can expand it, we need to move the 1/3 to the front. So it's going to be 1/3 times everything else. So now we can expand the logarithmic expression. Now the 1/3 is going to be distributed to each of the three new logs. So it's going to be log x squared plus log y minus 4 log z, since z is on the bottom. For now, we'll leave it as log z to the 4th. The last thing we need to do is take the exponents and move it to the front. So the final answer is going to look like this. It's 1/3 2 log x plus log y minus 4 log z. This is it. That's how you can expand the logarithmic expression. But let's try another one. Try this practice problem. The first thing I would do is convert the radical expressions into exponents. The square root of y is y to the 1/2. The cube root of z to the 4th is z to the 4/3. So now we can expand the expression. So it's log x squared plus log y to the 1/2 minus log z to the 4/3. So now let's move the exponents back to the front. So the final answer is 2 log x plus 1/2 log y minus 4/3 log z. And that's it for this problem. Now let's simplify a few expressions. What is the value of ln1, ln e, and ln e to the 5th power? The natural log of 1, or the log of 1, is always 0. The natural log of e is always equal to 1. Now what do you think ln e to the 5th power is equal to? Notice that the 5, we can move it to the front. So ln e to the 5th power is 5 ln e. And keep in mind, ln e is 1. So this is simply equal to 5. Try these. E to the ln 7, e to the 3 ln x, and 2e 4 ln y. So what's e to the ln 7? Notice that the base of natural log is e. Whenever a base is raised to an exponent that contains the base of itself, those two bases will cancel, and the answer is simply 7. For this one, we need to take the 3 and move it to the exponent of x. E to the 3 ln x is the same as e to the ln x cubed. And so this is base e. These two will cancel, and it's simply x cubed. Now what about this one? This is the same as 2e to the ln y to the 4th. Now this part right here will change to y to the 4th. So the answer is simply 2 times y to the 4th. Try these two problems. So what is 5 raised to the log base 5 of y to the 8? So just like the last examples, these will cancel, and the answer is simply y to the 8th power. For this one, the 3's will cancel, and it's x squared plus 6. So you now know what to do if you ever see something like that on a test. Simplify the following log expression. How would you simplify it? What's log base 3 of 6 minus log base 3 of 2? Whenever you wish to subtract two logs, you can combine them into a single log by means of division. So it's equivalent to log base 3, 6 divided by 2. 6 divided by 2 is 3. Now what is log base 3 of 3? 3 to the what power is equal to 3? This is 3 to the first power. 3 to the first power is 3. So log base 3 of 3 is 1. Keep in mind, you could change it to, you can use the change of base formula. Log base 3 of 3 is the same as log 3 over log 3, which cancels and give you 1. Let's try another example. Try this one, log base 2 of 12 plus log base 2 of 24 minus log base 2 of 9. So feel free to pause the video and see if you can get the answer. So let's combine it into a single log. So the 12 and the 24 are associated with a positive sign. So it's going to be 12 times 24 on top. The 9 is associated with a negative sign. So we're going to put a 9 on the bottom. So what we need to do is simplify this expression. So what's 12 times 24 divided by 9? Let's break it into smaller numbers. 12 is 4 times 3, 24 is 8 times 3, and 9 is 3 times 3. So we can cancel the 3's, and 4 times 8 is 32. So what we really have is log base 2 of 32. Now how many 2's do we need to multiply to get to 32? Keep in mind 2 to the 5th power is 32. So log base 2 of 32 is 5. Here's another one. Log base 7, 1 over 6, plus log base 7, 6 over 49. So what can we do in this particular problem? How can we solve it? So just like before, since we have two logs separated by an addition sign, we're going to combine it into a single log by multiplying what's on the inside. So it's 1 over 6 times 6 over 49. Notice that the 6's, they cancel. And so what we have left over is log base 7 over 1 of 1 over 49. So we know that 7 squared is 49. So therefore 7 to the negative 2 power is 1 over 49. Therefore this expression is equal to negative 2. So that's the answer. Sometimes you need to change an expression from logarithmic form into exponential form. How can we do that? 2 to the 3rd power is equal to 8. And that's how you can do it. Try this one. 3 to the 2nd power is equal to 9. 5 squared is equal to 25. So that's a simple way in which you can convert a log expression into exponential form. Try these two. Log base A of B is equal to C, and log base 2 of X is equal to Y. So A raised to the C is equal to B. That's how you can change it to exponential form. 2 raised to the Y is equal to X. So now let's convert back to logarithmic form. Convert each exponential equation into a log. So what this really means is log base 3 of 27 is equal to 3. If you work backwards, 3 to the 3rd is 27. So So the exponent always goes across the equal sign. The base that has the exponent is the base of the log. So this expression, the next one, 2 to the 4th is equal to 16, is the same as log base 2 of 16 is equal to 4. So the exponent is what the log is equal to. And this is the base of the exponent, which is the base of log. So here we have log base 3 of 18 is equal to x. So x is the exponent and the base is 3. Now let's spend some time solving logarithmic equations. Log base x of 27 is equal to 3. Solve for x. So let's convert it to exponential form. X raised to the third power is 27. So clearly we can see x is 3 because 3 to the third is 27. Therefore x is equal to 3. Try this one. Log base 2 of y is equal to 5. So if we convert it to exponential form, 2 raised to the 5th power is equal to y. 2 to the 5th power is 2 times 2 times 2 times 2 times 2, 5 times. 2 and 2 makes 4, and 4 times 4 is 16. 16 times 2 is 32. So y is equal to 32. Try this problem. Go ahead and solve for x. Feel free to pause the video as you work through these examples. 2 to the third power is equal to what's inside. So 2 to the third power is equal to x plus 5. 2 times 2 times 2 is 8. So to solve for x, all we need to do is subtract both sides by 5. And 8 minus 5 is 3. Therefore x is equal to 3. Let's try another problem like that. Log base 3 of 2x minus 3 is equal to 2. So 3 raised to the second power equals what's inside. So 3 squared is equal to 2x minus 3. 3 times 3 is 9. So now we just need to solve for x. Let's add 3 to both sides of the equation. 3 plus 9 is 12. Since 2 is multiplied to the x, to separate the x from the 2, we need to perform the opposite of multiplication, which is division. So we need to divide both sides by 2. 12 divided by 2 is 6, and therefore x is equal to 6. Try that one. So what do you think is the first thing we need to do to solve for x? What we should do is condense the two logs into a single log by means of multiplication. So it's log base 2 times, or log base 2 of x minus 3 times x minus 1 is equal to 3. So now we can convert it to exponential form. 2 to the third power equals what's inside. So 2 to the third power is equal to x minus 3 times x minus 1. On the right side, we need to FOIL. X times x is x squared, and x times negative 1, that's negative x. Negative 3 times x is negative 3x, and negative 3 times negative 1, that's plus 3. 2 to the third power is 8. So now let's combine like terms on the right side. Negative 1x and negative 3x. When added, they will change to negative 4x. So now we need to make some space. I might need the original expression. So let's subtract both sides by 8. If we do that, we will get a 0 on the left side, and on the right side, 3 minus 8 is negative 5. So we need to factor the trinomial. which has the leading coefficient of 1. So you need to look for two numbers that multiply to -5, but that add to -4. What are those two numbers? The two numbers are -5 and 1. -5 times +1 is -5, and -5 plus 1 is -4. So we can simply factor it like this. It's going to be x minus 5 times x plus 1. So now we could solve for x. Let's set each factor equal to 0. So x minus 5 is equal to 0, and x plus 1 is equal to 0. So for this equation, we need to subtract 1 from both sides, but here we need to add 5. So x is equal to 5, and x is equal to -1. So now, when dealing with logs, you need to find out if you have any extraneous solutions. So, are both of these answers acceptable, or do we have an extraneous solution? So keep in mind, you can never have a negative number inside a log. So if we plug in 5 into x minus 3, 5 minus 3 is +2, that's okay. If we plug in 5 here, 5 minus 1 is 4, that's okay. But if we plug in -1, -1 minus 3, that's -4. Log base 2 of -4 doesn't exist. So -1 is not in the domain of the log function. So therefore, x can't equal -1. This is the extraneous solution, and this is the actual solution, the one that we want. So the answer is x is equal to 5. Sometimes you might get a problem that wants you to identify the extraneous solution, which is this one. Try this one. Log base 3 of 2x plus 1 plus log base 3 x plus 8, and let's say that's equal to 3. Feel free to pause the video and work this problem. So let's combine the two log expressions into a single log. So we need to multiply 2x plus 1 and x plus 8. So now let's change it to exponential form. 3 to the third power is equal to what's inside. So 3 to the third is equal to 2x plus 1 times x plus 8. 3 to the third, that's 3 times 3 times 3, that's 27. And now we need to FOIL. 2x times x is 2x squared. 2x times 8 is 16x. 1 times x, that's x. And 1 times 8 is 8. So now let's add like terms. 16x plus x. That's equal to 17x. So let's subtract both sides by 27. So 0 is equal to 2x squared plus 17x. 8 minus 27, that's about -19. So let's see if we can factor this particular expression. How would you factor 2x squared plus 17x minus 19? So notice that we have a trinomial where the leading coefficient is not 1. So we have to take into account the 2. Multiply the leading coefficient by the constant term. That's 2 times -19. And that gives you -38. What two numbers multiply to -38 but add to +17? That's going to be +19 and -2. 19 times -2 is -38, but 19 plus -2 is +17. So what we're going to do is we're going to replace the middle term with -2x and 19x. Now at this point, what you want to do is you want to factor by grouping. you want to factor out the GCF, the greatest common factor, from the first two terms. So what can we take out from 2x squared and 2x? The most that we can take out is a 2x. 2x squared divided by 2x is equal to x, and negative 2x divided by 2x is equal to negative 1. Now from 19x and negative 19, we can take out a 19. 19x divided by 19 is equal to x. Negative 19 divided by 19 is equal to negative 1. Notice that we have a common factor, x minus 1. When you see that, that means you're on the right track. So let's factor out x minus 1. Now what's going to go inside the second parentheses? It's going to be what's outside of x minus 1, the 2x and the plus 19. So we can put that here. So now we can solve for x. So let's set each factor equal to 0, and let's solve. Here we need to add 1 to both sides. So our first answer is x is equal to 1. For the next one, we need to take away 19 from both sides. So 2x is equal to negative 19. And then we need to divide both sides by 2. So the other answer is x is equal to negative 19 over 2. So we can clearly see that we can plug in 1 into 2x plus 1 and x plus 8. And that's not going to give us any negative answers. However, if we plug in negative 19 over 2, that's like negative 9.5. Negative 9.5 plus 8 is negative 9.1. So this is an extraneous solution, so we can get rid of it. So the answer is 1. Now let's check the work. Let's see if we have the right answer. Let's see if it's correct. So let's plug in 1 into the equation. So it's going to be 2 times 1 plus 1, and on this side 1 plus 8. So 2 times 1 is 2 plus 1, that's 3. So we have log base 3 of 3. 1 plus 8 is 9. Now log base 3 of 3, the 3's cancel, so it's simply 1. What's log base 3 of 9? 3 squared is equal to 9, so this is equal to 2. And 1 plus 2 is 3. So which means that x is indeed equal to 1. Both sides of the equation have the same value. So here's another one. Log base 2 x plus 6 minus log base 2 x minus 8 is equal to 3. Go ahead and solve for x. So because we have a minus sign, it's going to be division. So when we combine it into a single log, it's going to be x plus 6 on top and x minus 8 on the bottom. And this is equal to 3. So 2 raised to the third power is equal to what's inside. Two to the third power is the same as 8, and we can write it as 8 over 1. So 8 over 1 is equal to x plus 6 divided by x minus 8. So let's cross multiply. 8x minus 64, that's 8 times x minus 8. And then 1 times x plus 6 is simply x plus 6 on the other side. So let's subtract both sides by x, and simultaneously let's add 64 to both sides. So the x variables will cancel, and that too. 8x minus 1x is 7x. 6 plus 64 is 70. So if we divide both sides by 7, 70 divided by 7 is 10. Therefore, x is equal to 10. Consider this example. Log base 2 of x plus 5 is equal to log base 2 of 3x minus 9. How can we solve for x in this particular example? Notice that we have the same base, same log, therefore what's inside should equal each other. It turns out that x plus 5, we could set it equal to 3x minus 9. Whenever you have a log equivalent to another log on the other side of the equation, you could set the inside equal to each other if they have the same base. So let's subtract both sides by x, and at the same time let's add 9 to both sides. So 5 plus 9 is 14. 3x minus 1x is 2x. So 14 divided by 2 is 7, therefore x is equal to 7. How would you solve for x? Let's say ln x is equal to 5. What is the value of x? So what you need to know is the base of the natural log. The base of the natural log is e. And if we convert it to exponential form, e raised to the 5th power is equal to x. And so we have the value of x is e raised to the 5th power. Try this one. Ln x plus 3 ln x is equal to 0. So if you don't see a coefficient, it's a 1. 1 plus 3 is 4. So 4 ln x is equal to 0. If we divide both sides by 4, 4 divided by 4 is 1. So we simply have ln x on the left side. 0 divided by 4 is 0. So e raised to the 0 is equal to x. Anything raised to the 0 power is 1, so x is equal to 1. Keep in mind, natural log of 1 is 0. Here's another example you can work on. If the natural log of x minus 3 is equal to 2, what is the value of x? So for this example, let's convert it to exponential form. E squared is equal to x minus 3. So to solve for x, we simply need to add 3 to both sides. So x is equal to e squared plus 3. Now sometimes you might be given exponential equations to solve. How would you solve for x in this particular equation? What you want to do is see if you can convert the bases into a common base. The common base of 8 and 16 is 2. 2 to the 3rd power is 8. 2 to the 4th power is 16. So we can replace 8 with 2 to the 3rd and 16 with 2 to the 4th. Now what happens when you raise one exponent to another? Whenever you raise an exponent to another exponent, you should multiply them. So 3 times x plus 4 is 3x plus 12. 4 times 2x minus 3 is 8x minus 12. So now we could solve for x. Since the bases are the same, the exponents must be the same. Therefore, 3x plus 12 must equal to 8x minus 12. So we could solve for x. Let's add 12 to both sides, and let's take away 3x from both sides. 12 plus 12 is 24. 8x minus 3x is 5x. So therefore, x is equal to 24 over 5. Now it's your turn. Try this example. So what is the common base of 9 and 27? It turns out that 3 squared is 9, and 3 to the third power is 27. So let's replace 9 with 3 squared and 27 with 3 to the third. And let's multiply the exponents. So 2 times 2x minus 1, that's going to be 4x minus 2. And 3 times 3x plus 6, that's 9x plus 18 if we distribute the 3. So now we can set the exponents equal to each other. So 4x minus 2 is equal to 9x plus 18. So let's add 2 to both sides, and let's take away 9x from both sides. So 4x minus 9x is negative 5x. 18 plus 2 is 20. So if we divide both sides by negative 5, x is equal to negative 4. And so this is the answer. How would you solve for x? What is the answer? We know that 2 squared is 4, and 2 to the third power is 8. So x has to be somewhere between 2 and 3, because 7 is between 4 and 8. So x is like 2 point something. But how can we find the value of x? We can't change 7 into a base 2. So in this particular instance, to solve for x, you want to use logs. You can use a log or a natural log. You'll get the same answer. So I'm going to take the natural log of both sides. Once I do that, I can take the x variable and move it to the front. So x, ln 2, is equal to ln 7. So to solve for x, divide both sides by ln 2. So now we have the answer. X is equal to the natural log of 7 divided by the natural log of 2. So at this point, you need a calculator. ln 7 divided by ln 2, you should get about 2.80735. Now you can check your work. If you type in 2 raised to the 2.80735, the answer should be close to 7. Once I type it in, I get 6.999976, which is approximately 7. So this technique works. So that's how you can solve for x when it's an exponent. You can use logs or natural logs. Try this one. Go ahead and solve for x. So if the base is e, you should definitely use natural log as opposed to the regular logs. So let's take the natural log of both sides. And the reason why you want to use the natural log is because ln e is 1. Now let's move this to the front. So we have x plus 2 times ln e is equal to ln 8. And we said ln e is 1, so this disappears. So we simply have x plus 2 on the left side. X plus 2 times 1 is x plus 2. So all we got to do is subtract both sides by 2. And the answer is x is equal to ln 8 minus 2. Consider the function f of x is equal to natural log 2x minus 6. If you're given this function, how can you find the domain of this function? Now keep in mind y is the same as f of x. So you can view this equation as y is equal to natural log 2x minus 6. So what is the domain? Now, you need to remember that you can't have a negative number or a 0 inside a log or a natural log. Therefore, 2x minus 6 must be greater than 0. So you can solve for x. So if we add 6 to both sides, 2x is greater than 6. and then if we divide by 2, we can see that x is greater than 3. So the domain is from 3 to infinity. And that's all you need to do if you only have one critical point. In this case, 3 is the critical point. But let's say if you have two critical numbers, it's not as simple. For example, go ahead and find the domain for this function, the natural log of x squared plus 2x minus 15. Feel free to pause the video, take a minute, and see if you can find the domain for that function. So the first thing I would do is set the inside greater than 0. So let's solve for x. We need to factor. What two numbers multiply to negative 15 but add to the middle coefficient 2? This is going to be negative 3 and positive 5. Negative 3 times 5 is negative 15, but negative 3 plus 5 is positive 2. Since the leading coefficient is 1, we could simply write it as x minus 3 times x plus 5. So there's two critical numbers, 3 for x and negative 5 for x as well. But how do you use those numbers to determine where the function is going to be greater than 0 or less than 0, particularly the inside part of the function? Since we have two critical numbers, what we need is a number line. We need to create a sign chart. We got to test the numbers to see what works and what doesn't. So the first critical number is negative 5, and the second is positive 3. Don't forget to switch the signs. If you solve for each one, if you set x minus 3 equal to 0, x will be plus 3. If you set x plus 5 equal to 0, and if you solve for x, x is negative 5. So you have to change the signs. All the way to the left, we have negative infinity, and all the way to the right, we have infinity. So let's plug in some test points. If we plug in a number between 3 to infinity, let's say if we plug in 4 into this expression, is it going to be positive or negative? So 4 minus 3 is a positive number. 4 plus 5 is a positive number. Whenever you multiply two positive numbers, you will get a positive result. So let's put a plus for this region. Now pick a number between negative 5 and 3. Let's use 0. So 0 minus 3 is negative. 0 plus 5 is a positive number. Whenever you multiply a negative number and a positive number, you're going to get a negative number. Now, if we plug in a number between negative 5 and negative infinity, let's say negative 6. Negative 6 minus 3 is negative. Negative 6 plus 5 is negative. Two negative numbers, when multiplied, will give you a positive number. So keep in mind, we want the portion of this equation that is greater than 0. That means the positive part and not the negative part. So we want this region and this region. And that's where the equation works. Anywhere between negative 5 and 3, the function will have a negative value, and you can't have a negative number inside a natural log. So it's not going to work in this region. So therefore, the domain, you can literally see it. It's going to include this region and this region. So the domain is from negative infinity to negative 5 union 3 to infinity. Now, does it include 5 or should we exclude it? Notice that it's greater than 0, not greater than or equal to 0. So we have an open circle at negative 5 and 3. Therefore, we should use parentheses and not brackets at negative 5 and 3. So that's how you can find the domain of a natural log function or even a log function. So if you have one critical number, simply set it greater than 0 and solve for x, you're done. If you have two or more critical numbers, you need a number line or a sign chart to figure this out. Consider the function ln x plus 3 minus 1. Given this function, how can you find the inverse function? what do you need to do? What steps do you have to take? So the first thing you want to do is replace f of x with y. F of x and y are the same thing. Your next step to find the inverse function, you want to switch x and y. So x is equal to ln y plus 3 minus 1. After that, you want to solve for y. So let's add 1 to both sides. So x plus 1 is equal to ln y plus 3. To get rid of the natural log, we need to convert it to exponential form. So e raised to the x plus 1 is equal to what's inside. So therefore, we have this equation. E to the x plus 1 is equal to y plus 3. So now the last thing we need to do is subtract 3 from both sides. So y is equal to e raised to the x plus 1 minus 3. At this point, you can replace this y with the inverse function symbol. So f to the negative 1x, which is the inverse function, is e to the x plus 1 minus 3. And so this is the answer. And by the way, notice that natural log functions and exponential functions are inversely related. As you can see, we started with a natural log function, and the inverse function was an exponential function. So what we're going to do at this point is we're going to graph a few exponential functions and then a few logarithmic functions. So let's start with y is equal to 2 raised to the x minus 3 plus 1. So what do we need to do to graph the function? Let's take the exponent and let's set it equal to two numbers, 0 and 1, and solve for x. If x minus 3 is equal to 0, x is equal to 3. And if x minus 3 is equal to 1, x is 4. Now those points I'm going to choose for my table. I'm going to choose 3 and 4. So what is the value of y when x is 3? So 2 raised to the 3 minus 3 plus 1. 3 minus 3 is 0. Anything raised to the 0 power is 1, so this is equal to 2. So when x is 3, y is 2. Now what about when x is 4? What is the value of y? So 2 raised to the 4 minus 3 plus 1. 4 minus 3 is 1, 2 to the first power is 2, and 2 plus 1 is 3. So we have the point 4 comma 3. This number that you see on the outside, the plus 1, that's the horizontal asymptote for the exponential function. Exponential functions have horizontal asymptotes. Logarithmic functions have vertical asymptotes. So the equation for the horizontal asymptote is y is equal to 1. Once you have the asymptote and 2 points, you have all that you need to graph the exponential function. So let's plot the horizontal asymptote at y equals 1. And then we have the point 3 comma 2, which is over here, and 4, 3, which is around this area. So the graph starts from the horizontal asymptote, and then it follows the 2 points. The exponential function is an increasing function that goes up at an increasing rate. The logarithmic function is an increasing function that increases at a decreasing rate. Let's try another exponential function. Go ahead and graph this one. So just like before, we're going to set the exponent equal to 0 and 1. So if x plus 1 is 0, that means x is negative 1. And if x plus 1 is equal to 1, x is 0. So we need to plug in 0 and 1 into the equation. And let's find the values of y. So e to the negative 1 plus 1 minus 2. Negative 1 plus 1 is 0. anything raised to the 0 power is 1. So 1 minus 2 is negative 1. Now, if we plug in 0 for x, 0 plus 1 is 1. And so we simply have e minus 2. So keep in mind, e is approximately about 2.7. So 2.7 minus 2 is about 0.7. Lastly, we need the horizontal asymptote, which is basically this number next to e. So it's y is equal to negative 2. So this is where the horizontal asymptote is, at negative 2. And we have the points negative 1, and 0.7, which is around here. So the graph is going to start from the x-axis, and then it's going to increase in that direction. So now let's say if you have a graph that looks like this. It's 3 minus 2 to the 4 minus x. Try this one. So let's set 4 minus x equal to 0 and 1. So if we add x to both sides, this is supposed to be a 1. 4 is equal to x, and for the other one, we have 4 is equal to 1 plus x, if we add x to both sides. So here we got to take away a 4. So x is equal to 4, and also x is equal to 3. So our table should have 2 points, 3 and 4. 4 minus 3 is 1, and 4 minus 4 is 0. So now let's plug in the points into the equation. So 3 minus 2 times 4 minus, let's start with 3. So 4 minus 3 is 1. 3 minus 2 is also 1. So when x is 3, y is 1. Now if we plug in 4, it's going to be 4 minus 4, which is 0. 2 to the 0 power is 1. 3 minus 1 is 2. When you do it this way, you will always get numbers that you can work with. Now, what is the horizontal asymptote for this graph? The horizontal asymptote is the number outside of the exponential part of the function. So it's positive 3. Y is equal to positive 3. Don't let this negative sign confuse you. That sign is for the 2. In front of the 3, it's positive, so that's why it's positive 3. So now let's graph it. So let's start with the horizontal asymptote at y equals 3. And then we have the point 3, 1, which is over here, and also 4, 2. Now keep in mind, the graph always starts from the horizontal asymptote. This time, it's going to start here and go this direction. So notice that we have a negative sign in front of the x. When you see that, it reflects over the y-axis. And also we have a negative sign in front of the 2, which reflects over the x-axis. So let me give you all the different shapes and their transformations. So if you have y is equal to positive 2 raised to the positive x, so when x and y are positive, let's say this is for x and this is for y. X and y are positive in quadrant 2. I mean, not quadrant 2, excuse me, quadrant 1. So the graph is going to go towards quadrant 1. Now, when y is positive, but when x is negative, it's going to go towards quadrant 2. So it goes this way. In quadrant 2, x is negative, you got to go to the left, but y is positive because you're going up. Now, what quadrant is it going to go to if y is negative but x is positive? In this case, it's going to go towards quadrant 4. Because x is positive towards quadrant 4 because you're going to the right, and y is negative because you're going down. Now what about when x and y are both negative? Then it's going to go towards quadrant 3, which is the example that we have. In quadrant 3, you're going to the left because x is negative and you're going down, so y is negative. So it's a reflection about the origin, so to speak. Whenever you reflect over the x-axis and the y-axis, it's the same or equivalent as reflecting over the origin. So let's move on to the graphs of logarithms. How can we graph it? So for logs, set the inside part, the x minus 3, equal to three things: 0, 1, and whatever the base is. In this case, the base is 2. So we're going to set it equal to 2. Now, when you set it equal to 0, it's not going to give you a point. Rather, this is for the vertical asymptote. So if you add 3 to both sides, you can see that the vertical asymptote is at x equals 3. Now, the other 2 points is for the table. So if x minus 3 is 1, if we add both sides, if we add 3 to both sides, 1 plus 3 is 4. So we get the point 4 for x. And if x minus 3 is 2, if we add 3 to both sides, 2 plus 3 is 5. So x is 5. So now let's plug in these points. Four minus 3 is 1. Log of 1 is always 0. And 0 plus 1 is 1. Now let's replace x with 5. 5 minus 3 is 2. Log base 2 of 2, because the numbers are the same, they're going to cancel. It's simply 1. So 1 plus 1 is 2. When you do it this way, typically your y values will be integers. So now we have enough information to graph the function. So the vertical asymptote is at x is equal to 3. And we have the point 4, 1. And we have the point 5, 2. So this time, instead of starting from a horizontal asymptote, the graph is going to start from the vertical asymptote, and it's going to follow those 2 points. So it's going to go like this. And so that's how you can graph a logarithmic expression. Now, what is the domain for this function? Notice that the lowest x value is 3, and the highest is infinity. So the domain is from 3 to infinity. Now, what about the range? The range for a logarithmic function, or even a natural log, is always negative infinity to infinity. It's always going to be the case. Now, let's briefly go back to the exponential function that we had in the beginning. So we said that it had a horizontal asymptote at y equals 1, and it was an increasing function. I'm going to draw a rough sketch. It was something like this. What is the domain and range for this function? I forgot to mention that earlier. So the domain for an exponential function is always going to be all real numbers. The range for a logarithmic function is all real numbers. The range for an exponential function is limited. It's limited by the horizontal asymptote. The lowest y value is 1, and the highest goes all the way to infinity. But it doesn't touch 1, so it's 1 to infinity, but doesn't include 1. So now there was another exponential equation that looked like this. So we had a horizontal asymptote at 3, and because x and y are negative, this graph is going to start from the horizontal asymptote and go towards quadrant 3. So what is the domain and range for this function? Because it's an exponential function, the domain is all real numbers. The range, however, is different. The lowest y value is negative infinity because the function is going down. The highest is the horizontal asymptote, 3. So the range is from negative infinity to 3, not including 3. Try this one. Natural log x minus 1 plus 2. Go ahead and graph the equation. So we're going to set the inside equal to 0, 1, and the base. The base of a natural log is e. And let's make the table. So for the first one is for the vertical asymptote. That's the one where you set it equal to 0. So if x minus 1 is equal to 0, that means x is equal to 1. Now for the second two, if x minus 1 is equal to 1, if you add 1 to both sides, 1 plus 1 is 2, x is 2. And for the other one, it's going to be 1 plus e. So now let's find the y values that correspond to those points. So let's start with 2. Natural log of 2 minus 1 plus 2. 2 minus 1 is 2. 2 minus 1 is 1, not 2. Log of 1 is always 0. So 0 plus 2, we have the point 2 comma 2. Now let's plug in 1 plus e. So 1 plus e minus 1 plus 2. So the 1's will cancel. And we're simply going to have ln e. Ln e is always equal to 1. 1 plus 2 is 3. So we have the point 1 plus e comma 3. Now keep in mind, e is 2.7. So 1 plus 2.7, the x value is about 3.7. So now let's graph it. So we have a horizontal asymptote at y equals 2. Actually, not a horizontal asymptote, I take that back. You only have horizontal asymptotes for exponential functions. I'm looking at this number, but we have a vertical asymptote at 1. Logarithmic functions always have vertical asymptotes. And then we have the point 2 comma 2, which is over here, and then 3.73, which is roughly about there. So the graph looks something like this. So what is the domain and range? The range for a logarithmic function is always negative infinity to infinity. As you can see, the lowest y value is negative infinity and the highest is positive infinity. Now for the domain, it's restricted. The lowest x value is the vertical asymptote. So it starts at 1. And the highest x value is positive infinity. So the domain is from 1 to infinity. Try this. Log base 3, 2 minus x plus 1. So what I want you to do for this example, graph the equation, find the asymptotes, and then also graph the inverse function. So let's begin. Let's set the inside of the log equal to 0, 1, and the value of the base. In this case, the base is 3. So let's make our table. The vertical asymptote is for the first one. So if 2 minus x is 0, x has to be 2, because 2 minus 2 is 0. If 2 minus x is 1, x is 1. 2 minus 1 is 1. Now what about when 2 minus x is 3? What is the value of x? So if we subtract both sides by 2, negative x is 1, which means x is negative 1. So now let's find the y values that correspond to those points. 2 minus 1 is 1. Log of 1 is always 0. So 0 plus 1 is 1. Now let's plug in negative 1. 2 minus negative 1, that's the same as 2 plus 1, which is 3. Log base 3 of 3, the 3's cancel, you get 1. 1 plus 1 is 2. So now let's graph it. So the vertical asymptote is at 2, and we have the points 1, 1, which is over here, and negative 1, 2. So the graph is going to start from the vertical asymptote and it's going to follow these 2 points, which I need to do that one more time. So it's going to look like this. Notice that we have a negative in front of the x and a positive in front of the log. So negative x, positive y, that's quadrant 2. So it's going to go to the left and up. Now let's go ahead and graph the inverse function. The vertical line for the original function is x is equal to 2. For the inverse, we need to switch x with y. So the horizontal asymptote, it's going to be y is equal to 2 for the inverse function. So instead of x is equal to 2, it's now y is equal to 2. Now notice that the points that we have is 1, 1. So if you switch x and y, we're still going to get a point at 1, 1, but I need to use a different color. So I'm going to use yellow for the inverse function. Now for the second point, negative 1, 2, we need to change it to 2, negative 1. So x is 2, y is negative 1. So 2, negative 1 should be somewhere in this region. So to plot the exponential function, we need to start from the asymptote, and it's going to follow these 2 points. It's not bounded by the vertical asymptote. Notice that those 2 graphs, the one in green and yellow, they're symmetrical about the line y equals x, which is true of any inverse function. Now, if we had a typical log, let's say this is the vertical asymptote at x equals 2, and let's say the function went this way instead. For the exponential function, which is the inverse of a log function, it's going to go like this. So you could see the symmetry across this line. So this is y is equal to log, probably like x minus 2. And for this one, it's e to the x plus 2. And so those 2 functions are inverses of each other. They're symmetrical about the line y equals x. They reflect across that line. So that is it for this video. Thanks for watching.